Welcome students, welcome to the course on AIML Materials Engineering, and we are going to start lecture number 7. So far we have learned some basic aspects of material science engineering. I will elaborate on more on this. Okay, so first and foremost thing is we have to do some recap. What you have learned we should be revisiting again. That is mainly because you can recollect the things which you have already learned in a short. So, basics of material science, I have been tracing this again and again, depends on this correlation between processing, structure and the property. If you want to make any components, you have to follow some steps, and these are called processing steps. Depending on the type of processing route and steps involved, the structure will change, and the change of structure will lead to change of properties. So, therefore, this correlation between this processing, structure and property is what we need to understand. First we learn structure, then we will learn a little bit of properties, and finally we will learn the processing and how these three are correlated. You will be able to get then and then only. So, next thing we have learned is type of materials. We know that material walls can be massive. Already you have seen we have metals, polymers, ceramics, composites. We can divide into two broad categories, metals and non-metals. Under metals we have seen we have ferrous and non-ferrous. This division is mainly because ferrous metals, which are based on iron, nickel, cobalt, they are used in large quantity in actual applications. That is why they are taken separately, and other things are put together as non-ferrous metals. Under non-metals you can have ceramics, polymers or plastics. Better to call it a polymer because plastic is a subcategory of polymer. So, I would like to tell about that this is nothing but a polymer, better to call. And then you have composites, which are mixture or other combinations of metals, ceramics, polymers. So, this is our world and we are learning about that. Ferrous, I told you most important ferrous thing is steels, and that is what we extensively use in real applications. They are nothing but iron carbon alloys with carbon content varying from very low like 0.028% to about 1%. Theoretically speaking, this is what is the definition or range of carbon concentration given 0.02 to 28%, but practically we have never seen any steels which has more than about 1%. That is why the carbon concentration will vary from 0.02 to about 1%. And based on different elements present in the steels, we can divide into plain carbon steels or alloy steels. Plain carbon steels will not have many elements added, but it will have some impurities like sulfur, phosphorus, manganese, silicon. That has come because of the processing of seals. And alloy steels will have other alloying elements added like stainless steel has chromium and nickel, and other steel like tool steel has elements like molybdenum, chromium, etc. And these steels are basically based on the classic iron carbon phase diagram. I will not discuss on these kind of aspects because that will take us a lot of time, but for you to know that basis of steels and cast iron is basically this diagram which you are seeing on your screen now, and this is nothing but a pure iron in which carbon is added. Small amount of carbon is added, it varies from 0 to about 6.6 weight% of carbon. That corresponds to the iron carbide, which is nothing but Fe3C, and Fe3C is basically a major phase in steels and the cast irons. Mostly in steels actually Fe3C is present in as an important material phase or in the microstructure. So, but as you add carbon, carbon can also get into iron lattice or the crystal structure of iron lattice. That is why actually this is very important, and this is something which we have learned from the last lecture also, and we will learn more here. So, there are two types of phases which forms in the alloys predominantly. These are two types, one is called solution, other is called compounds, and Fe3C is a compound, as you can understand. It is basically a compound between iron and carbon with a very fixed chemistry, iron 3 and carbon. So, 3 atoms of iron in its shell, 1 atom of carbon on an average. On the other hand, solutions are like liquid solutions. You can add sugar into water, salt into water, mix them together, or glucose into water. That is nothing but a liquid solution. Can you have the same thing in solid state? Yes. You can add nickel in copper or vice versa. You can add copper into nickel also. They will mix nicely together and form a solid solution. So, what actually happens when you add nickel into copper? Nickel atoms actually go and replace the copper atom in the FCC copper structure. Same thing happens when you add copper into nickel. So, that is how this whole range of solutions actually form. And we talked about it. This is very important concept because solid solutions are widely used in the actual material in alloys. And you can have two types of solid solution. One is substitutional solution, other is interstitial solution. In substitutional solid solutions, you are replacing the solvent atom by solute, and as you know, the sizes of the atoms will be similar. Difference may be maximum 15%. There are rules, defined rules under which the solid solutions can form. I will not go into details of that, but then you have a interstitial solid solution in which a small atom can go to the interstitials like tetrahedral or octahedral voids. Steel is exactly like that. Carbon is a smaller atom than iron. It goes into interstices of iron lattice and they form solid solution. And these are very widely have been studied. You can also have intermetallics or compounds. We call intermetallic because they are between two metals. Like let us talk about this one, like nickel aluminum alloy, which is widely used also in various applications, especially in engine applications, aero engine applications. And I talked about it. There are different compounds here: Ni3Al, NiL, Ni5Al3, Ni2Al3, NiL2. Also on both the ends of the phase diagram, we have FCC nickel solid solution, FCC aluminum solid solution. So, compounds will have either fixed stoichiometries or it will have a variable stoichiometry also, like NiL has a variable stoichiometry. But specific compound like Ni5Al3 or NiL3 has a fixed composition, you can't change it. So, this is what we learned in the last lecture, and Ni3L is used as a material for jet engines. We discussed about it a lot in the last lecture. Well, I talked about alloy steels. To give you an example, stainless steel is an alloy steel with chromium and iron, nickel, other than iron and carbon present in these alloys. They have other alloying element present in this. You can also have cast iron in which carbon concentration is higher than steels, something like about 3 to 4% carbon. You have manganese and silicon also. It has a good corrosion properties in compression. They are brittle, but it has very high absorbing ability. So, we also discussed about some non-ferrous metals like aluminum, and aluminum is very important structural material used in aircrafts. Body of the aircraft is made of aluminum alloys like duralumin, and it is nothing but aluminum solid solutions in which the precipitates of copper and aluminum like CuL2 are present, or different variants of these are present. So, you can see these details of this in this book by Porter and Sterling, available in any online stores. Then we discuss about titanium. Titanium is very important for space industries and other industries, also implant in the body. It is strong, lightweight with a very high corrosion resistance, and it is although chemically active, it can react with oxygen, nitrogen very easily. It is difficult but costly to produce also. We talked about nickel titanium alloys which are used as same memory alloys in the last lecture. Other than that, we also have high temperature materials like alloys and ceramics. So, jet engines, gas turbine engines, rockets, nuclear applications require this. They need to have a high temperature strength, keep resistance, corrosion resistance at temperature higher than about 1100 degrees Celsius temperature. All of you probably know that even these re-entry vehicles which actually travels at a high speed, when the astronauts from the space station comes down to the earth, actually are made up of high temperature materials, mostly high temperature ceramics, because when it undergoes through the atmosphere, it passes through the atmosphere, a lot of frictional heat generates, and because of these, temperature can go even beyond 2000 degrees Celsius temperature, and that is why it can lead to accidents. We all know what happened to many of the astronauts during accidents. So, high temperature materials are very important, whether it is a metal or ceramic does not matter. And most important high temperature material is superalloys. they are actually nickel based alloys or iron based alloys. Nowadays cobalt based superalloys are also available, but they may not be used directly, but nickel based superalloys are directly used, and these actually contains many elements, that is why I call them superalloys. Some of the superalloys contains about 14 elements, and they are the ones which are used as the blades of the turbine engines. You can see here these blades of turbine engines are shown. You can clearly see that actually you can see that these are these blades, and the one is shown on the right hand side. They are the one who is used in the plane engines, but you can also have refractory metals. Remember the periodic table, right? That is the most important. In the periodic table there are elements like molybdenum, titanium, tungsten, niobium. They are actually, or rhenium, they are actually a very high melting temperature, more than 2000 degrees Celsius temperature. So these metals along with alloys of that widely used for different kinds of application at high temperatures. They are called refractory alloys. And to give an example, pure tungsten itself is used in the incandescent bulbs as a tungsten wire, and basically filament made it from the tungsten wire, and that is because tungsten can withstand very high temperature, and when current passes through the tungsten coil it glows and produces light. Similarly, you can have other alloys like tungsten, nickel alloys, niobium alloys, nickel, niobium, chromium alloys. They are all used widely in the high temperature applications. Let us talk about a little bit about ceramics. As I told you, ceramics are basically compounds, but the compounds not between metals, but compound between metallic and non-metallic elements, and they can be either oxides, carbides or nitrides. These are the three types of things produced, and we know that there are different kinds of oxide exist in the world, like aluminum. It reacts with oxygen from aluminum oxide, which is nothing but a Al2O3. Okay, all of you should know that alumina, this is the formula of alumina. This is nothing but a compound between oxygen and aluminum. Zirconium oxide, zirconia, this is also a compound between zirconium and aluminum. You can also have titanium nitride, it is a compound between titanium and nitrogen. You can also have zirconium nitride. Okay. Then you have carbides like tungsten carbides, which is used as tool steels or insert in the cutting tools, or you can have zirconium carbide. So these are all compounds like that, oxide, nitrides, carbides, different kinds, and they have very high melting temperature, sometimes beyond even 2500 degrees Celsius temperature. They have huge compressive strengths, but poor tensile strengths. Mostly they are brittle. Most of the ceramics are brittle except few, and like carbides like silicon carbide, silicon nitride, they can offer moderate toughness. Similarly, if I add yttrium oxide into zirconium oxide, it can also give to toughening because of transformation toughening. They have low thermal and electrical conductivity. These properties you should remember, because when you are talking about application, properties are very important, and that is why these are actually considered very important. So I have given you the formula of this, like aluminum oxide, silicon dioxide. Silicon dioxide is widely known to people because silicon is produced from silicon dioxide, and earth crust has a lot of silicon dioxide present. Then you can have uranium oxide, which is used as a fuel for the nuclear power plants. Silicon carbide, titanium carbide, tungsten carbide, they are also widely used. Many of the cutting blades are made of silicon carbide, right. By the way, diamond is also considered ceramic because it has very high melting temperature, although it is made of pure carbon. Then you have titanium nitride, boron nitride, even clay like clarinite, body materials present in the bone, the hydroxyapatite, they are all part of ceramics. Another important ceramic is silicon ceramics, which are nothing but silicon, aluminum, nitrogen. You can see that it is stronger than steel, it is extremely hard, but very light because it has aluminum and nitrogen. Silicon is also not very dense. So that is why this kind of ceramics can be widely used for various applications. Well, let us talk about a little bit polymers. Polymers actually what? They are nothing but chains actually. So best example to realize polymer for any young person is basically looks like a bowl of spaghetti, and obviously if you add sauce into it, there will be binding, no. So it is basically a bowl of spaghetti, which is can be a model to understand polymer. And polymers can be different types. They can be thermoplastics, which you can mold many times. You can heat it up, make it liquid, and then mold it, form some compounds like different kinds of polymer gadgets are used nowadays, and then again you melt it back and produce that. That is why they are called thermoplastics. If you heat it up, they become very plastic. And then you have thermosets. Thermosets are opposite. They, if you heat it up, then it cannot be reused. They set for once, and it can be like bakelite is a thermoset which is used in the switches, power switches. Thermoplastic, there are many thermoplastic, polyethylene, polyvinyl chloride, they are all thermoplastics. And onto that you have plastics, okay. Because there are these plastics are different categories of things. They may not be thermoplastic or thermosets. And then you have finally have elastomers like a rubber, which you can expand at very large deformation can be possible by using elastomers. This all we know, okay. These are very simple thing which you know very well. That is what, but as I told, let us talk about a little about thermoplastic versus thermosets. Thermoplastic is solid at room temperature, they are viscous liquid at high temperature. That is what allows them to be given different steps. Heating and cooling cycles can be repeated. So, you can heat and cool, still material will behave same way, like nylon, acrylic, cellulose, PVC, polyvinyl chloride, PVC pipes all of you know, nylon as a rope so they are widely used, and they are the ones which constitute almost 70% of the polymer produced in the world. They can be molded, extruded, rolled, any shapes you can give, you can provide. On the other hand, thermosets, they soften very easily when you heat them, but harden on cooling, and when they harden they become an infusible solid. That means what? You cannot again reheat and get the same back. That is why thermosets are used for one time, and this curing reaction which happens during heating is irreversible. So, therefore, reheating will burn and char the material, it will produce only carbon. Examples are epoxies, phenolics, certain polyesters. We use knobs and handles of the pots and pans and light switches, the various applications of thermosets. But unlike thermoplastics, thermosets are not so widely used. You should remember the difference between these two very well, and probably you know it. On the other hand, elastomers, they undergo large elastic deformation when you subject to stresses, and rubber bands you have probably seen, you can actually extend at a very large distance. That is why we call that they undergo large deformation when they are subject to stresses. It retains original shape and size on removal of the stress, not always. If you deform extensively, it may not come back to the original shape, may come back to shape, but not the size. They can be made from natural rubber trees are available, you know that, or you can be made a synthetic. Okay, many of these tires of the cars are made of rubbery like material, they are synthetic. Additives can be blended, like sulfur is blended to obtain strength in the tires, that is called vulcanization of rubber. And the applications are corrosion and absorption protections, vibration, shock absorptions. You can use for actually electrical insulations, non-skid surfaces. Products are tires, footwear. See, all your footwears are made up of elastomers. Gaskets in the pressure cookers made up of elastomers. Seals, by which you can seal certain things. Even fluorines, polyvinyl, many of the fluorines are made up of rubbery things, or furnitures nowadays are made up of rubbery things. So, rubber is widely used, and they have very distinct properties, and there are reasons for it. So, fundamentally what is the main thing about of these polymers? Fundamentally what? Polymers are synthesized by joining very small units, they are called Mars. So, in the word polymer you can divide that, you have two words, poly and Mar. So, Mar is the unit, small molecular unit, and if you join them together they produce polymer, and therefore, when you join them together it will create a macromolecule, big molecule, right. So, like is considered ethylene C2H4, correct. If you join many of the ethylene molecules they form polyethylene, right. This is what you use everyday purpose, polyethylene bags. Okay, we call polyethylene bags, which are polyethylene actually. Polyethylene, that is what you use normally. So, what is polyethylene? You know probably very well. This is nothing but a polymerization of ethylene. So, polymers are that. Now, we can polymerize different ways. You can add and polymer. That is what is this. Nylon is exactly that. This is polyethylene. Yes, additive polymerization done. Nylon is a step polymerization. You can add this molecule step by step. That is what it is called polymerization. Remember, the formula of nylon is this. This has amine groups and also it has ethylene groups. Okay. So, that is what is about polymers, and if you want to know a little bit about that, addition polymers are like this. You can see there are monomers. Initiation has started, then one by one molecules are joining. Okay, molecules are basically joining one by one, you can see there, and then finally it forms a chain. On the other step polymerization, you have a n mer, you add one n plus 1 mer, then you add another one, you become n plus 2 mer, and like that. You can also have two different kinds of mer, one is one molecule, other one is other molecule, they can also join and form n1 plus n2 mers. So, that is the step polymerization. It basically formed by steps, very easy to understand, and not like a addition of one mer at a time. That is the difference between these two. So, that is what is there possessed, but you can also have different kinds of links in the polymers. Obviously, first one is the linear chain. You can see here this is a linear chain. You can also have a branch like a tree, you can see that branch chains. Then you can have a cross linked chains, you can see that there are two chains, they are cross linked, right. You can also have tidally cross linked chains, that means tertiary chains possible. It is primary, secondary, here you have primary, secondary, tertiary, all kinds of chains are possible. That is why I call tidally crossed linked chains. And this is very important, because if you want to create rigid structure of polymer, then you need to have a tidally cross linked chains. If you want to have a simple structure, linear one is most important, or you can go to branch structures also possible. So, that is how actually polymers actually formed, and different kinds of polymers have different ways of formation. You can also have different units of polymer, like homopolymer has single unit, like I told you about polyethylene, you have polyacetylene actually, this is C2H2N, okay. And so therefore, this is one kind of polymer. You can also have C2H3Cl, I think this is vinyl, so that is added. Then you can also have, compared to this is called homopolymer, that means one type of polymer molecule is chained, there is not more than one type of required, but in copolymers you can have more than one type of required, like in this case ethylene and butane, both are used actually. So, there are two types of molecules, one is this, other one is this one, this is one, this is another one, they are connected. You can have alternative arrangements like one after another, you can see it, you can have random also, you can have blocks or grafting possible. So, different kinds of arrangements are possible, alternative ones are widely seen, one after another. You can have random, it can add anywhere the second polymer, and you can have also block, second polymer is added as a block, or you can have also grafted possible. So, all kinds of this kind of things are possible in case of polymer, and that is something which is very made this polymers as a unique thing in the world. And in polymers you can have both crystalline part and amorphous part together. Crystalline part means when these chains are arranged very nicely, you can see here one by one they are parallelly arranged. You can also have arrangements of haphazard molecules, that is what we call as the amorphous regions, and this is very important in polymers, because most of polymers will have both the amorphous and the crystalline regions or amorphous regions predominantly. And so, we will try to understand now what is amorphous, what is crystalline in detail, but I think I have told you about the crystalline material. Crystalline materials have definite order of arrangement of atoms, and that is what you see BCC, FCC, HCP structures, and so that is a subtle feature of any crystalline materials, and that is borrowed here. Here you can see chains are arranged in a very definite way, parallel to one each other and orderly manner other, that is why they are called crystalline part of the polymers. But if the chains are in a haphazard way, then it will be amorphous polymers. So, let us stop here, we will come back to it in the next part of the lecture, that is where the amorphous and crystalline aspects will be very much clear to you. Thank you.